Sum and difference identities. Now this is where the this is real life right here.
Real life. Okay.
Yep.
Okay.
Because we're going to do it for real.
As opposed to all the fake math we've been doing lately.
Math, yes.
This guy. Section 5.3, sum and difference identities. The identities we're going to use throughout this section are up here. They are the sum and difference identities. There's one for sine, one for cosine, and one for tangent.
And they're all slightly on the unique side of things.
Right. So here's how you want to look at this. Basically, sine of this is an angle, and either you'll have a plus or a minus sign, depending on your problem. Yep. Then there's a different angle, equals, and then whatever these two angles are, you fill them in here and here. We've got a plus or minus here on sine, which gives us a plus or minus here. So if it's plus on the left,
it's got to be plus on the right.
For sine, yeah. And then for cosine, we've got the same setup on the left, just with cosine, but over on the right side, it is a little different.
It's a little paid, so pay attention here because
the cosines are paired up, sines are paired up.
And the sines, S-I-G-N-Es, those guys are upside down. So
right.
If I have cosine of u plus v, when I go through my identity, I'm going to have cosine u cosine v minus sine u sine v.
Because this upside down thing is saying it's the opposite of whatever it was on this side.
Right.
So then tangent kind of throws both of those things together, because if it's a plus for tangent, on top here we would have a plus, but on bottom we would have a minus. And the tricky thing with tangent is you can't always actually use the tangent one, just depending on what's going on.
Right, because you could end up with an undefined situation in the denominator.
Right, so another way you can do this actually is tangent of u plus v would equal, since tangent is, you know, sine over cosine.
Whoa, what the heck? That looks tricky.
It does.
That looks even more real life.
Yeah, so tangent is sine over cosine, so we can basically make, if it gives us tangent, we can make it sine over cosine.
Yeah,
just
and
keep
go
the
from
angle
there.
The same. So let's dive right in with example 1.
Let's do it.
The
exact value. I like that.
Okay, exact value means that you will have square roots.
Or some other thing in there.
Or fractions or something.
But
or
no decimals.
Both.
No decimals, though. This is not a calculator issue.
Right. Now, the deal with this is the sum and difference identities open up this whole new world of things we can find without our calculator. Before now, cosine of 15 degrees, we would have had to put in our calculator. But what we want to do is we want to look on our unit circle. We want to come up with two angles on the unit circle that if we either add or subtract them, we get 15.
I have an idea.
Okay, tell me what your idea is.
60 minus 45.
That's a good one.
I have another idea.
Okay.
45 minus 30.
Okay. And we could continue. Actually, there's a ton that when you subtract
I have another idea.
Them. Okay, yeah.
135 minus 120.
Are any of those answers any better than the first answer that we have here, cosine of 60 minus 40?
Well, I don't.
Are they? Would you say they're equally good?
Equally good, yes.
Just whatever you can come up with, basically, that either adds or subtracts to get
cosine of 15.
15. Okay.
Yeah.
So then
the choice is yours.
Then what we do is we would say that the 60 degrees is u, the 45 degrees is v. This minus sign is just going to tell us what signs to use up here in our identity. Okay? Right?
Yep. Perfect.
Right. So
perfect.
This equals cosine
of u, which is now the 60, or whatever angle you chose to be first.
If you chose a different angle to be first, you'd put that in instead of what we did.
Right.
And then we put cosine again with the other angle.
And just the angle. We don't need minus 45. The minus sign's accounted for
whenever I picked these.
Right. So we just need the actual number angle item.
Yes. And now we've got sine of 60 degrees, sine of 45 degrees. Well, we already have our unit circle out probably because we were like, oh no, what angle's on the unit circle? So that's another way that we can do this is we actually want to figure out what is cosine of 60 degrees.
Right.
And we can do that with our unit circle.
Right.
Or with special
I believe
triangles.
It's 1/2.
Let's see, cosine, yeah, that's 1/2.
Times the square root of 2 over 2 plus square root of 3 over 2 times the square root of 2 over 2.
That's amazing. You did all that without actually having a unit circle out.
Genius right here. Almost as genius as Mrs. Stevenson, but not
Well, I mean, yeah.
Wiser because of my age has been pointed out on numerous videos.
Square root of 3 times square root of 2?
Square root of 6. Not the square root of 5. or any other craziness that you try and come up with. And by the way, square root of 2 plus square root of 6, drum roll is?
Square root of 2 plus square root of 6.
You cannot put those together. Now, you can multiply them. You cannot add them.
Right, so here we were able to multiply those together. We did 1 times the square root of 2 and got the square root of 2, and 2 times 2 on bottom was 4 on each of these, and then they already have common denominators, so we can put them together, but this is our best answer.
And that's an exact answer.
That is an exact answer because we have square roots and fractions.
That is correct.
So that's, and these are all going to look pretty similar, like with just maybe signs changed up.
A little bit.
Yeah, a little bit, but you're going to see a lot of square roots of 2s and square roots of 6s in your answers on these.
Right, right.
So. All right, Mr. Hazelwood, BRB. We're going to continue on without him. Example 2, confirming cofunction identities. So you may have wondered when we started in 5.1, how did we come up with some of these identities? And for the cofunction identities, basically the way to prove them would be to use the sum and difference identities, or one way to prove them at least. You can... it should make sense that they go together because of what we did when we were working with graphing sine and cosine, like that cosine and sine are just shifts of each other. But to actually sit here and algebraically prove, we're going to use the sum and difference formulas. So they're not up here on my screen, but they are on your notes. So if you get confused about what I'm talking about, look back at those identities. Now, if we're using a sum and difference, the first angle is u in our identity, the second one is v. This is a minus sign, so I'm going to use the identity that has a plus in it over here. So I just fill in the right side of the cosine difference identity. Difference because it's negative. So that's cosine of pi over 2, cosine x. Since this was a minus, it's a plus. And then we do sine of pi over 2, sine of x. From there, we just need to actually simplify what we can. And since we have a unit circle, we can actually figure out cosine of pi over 2. Pi over 2 is 90 degrees, so that's up here. We look at that point on our unit circle and get that our cosine is 0 and our sine is 1. So that means that I can replace those. Cosine of pi over 2 is 0. So that's 0 times cosine x. Sine of pi over 2 is 1, so that's 1 times sine x. And that equals 0 times anything is 0, so that will cancel out right there. That'll just become 0. 1 times sine x is sine x. So we just proved what we wanted, so we're done with this proof for A. So that was pretty simple, pretty straightforward. You're just using that identity to come up with what is on the right-hand side here. So part B, we're going to do the same thing, but this time we're going to use sine and see what happens a little bit differently. So in this case, we have u and v, and we're using the sine identity. So the first identity on our paper, on this paper that we're on right now. So sine of pi over 2, and then it switches to cosine of the second angle, which is x. Since this is a minus sign, ours will also be a minus sign. And then we do cosine of pi over 2, sine of x. So we can still use this same thing to figure out what cosine and sine of pi over 2 are, conveniently enough. Sine of pi over 2 is 1. Cosine of pi over 2 is 0, which means that this cancels out, and we're just left with cosine x, which, if we look back up here, is what we wanted, so we are done with that proof as well. Example 3, using the sum and difference formulas. Example 3, using the sum and difference formulas. So these problems can look kind of tricky, but they're actually pretty simple because they just want us to match basically what we have here with the right side of a formula and change it into the left side. So to do that, we would realize here that this is u and v for our angles in one of our formulas, and then because sine and cosine, we have sine cosine and then cosine sine, that matches up best with sine. And since it's sine, if this is a plus, then inside of our parentheses we will have a plus. So we can rewrite this, which looks like the right side, we can actually rewrite it as the left side and get sine of 35 degrees. That's our answer. We don't have to, if we ended up with something that was on our unit circle, we could go ahead and figure out what that was, but if we don't, then we just leave it as sine of 35. So let's try the next one. We have cosine, cosine, sine, sine. So that matches up with a cosine identity for the sum and difference. We've got u and v. So we would write this as cosine of pi over 3. And then since this is a plus and it's cosine, we do the opposite, which is minus. So pi over 3 minus pi over 4. Now to combine these so that we have just a single angle inside, we do have to come up with common denominators. And so our common denominator for 3 and 4, we would want to have a 12. So to get this to be 12 on bottom, for our first fraction, we've got to make that be 4 pi over 12. For this to be a 12 on bottom, we have to multiply by 3, so that's 3 pi over 12. We're subtracting, which means that we get cosine of 1 pi over 12, and that's our answer because we don't have that value as on our unit circle, we just leave it alone. Now we would do, for this last one, sine x sine 2x minus cosine x cosine 2x. Keep in mind, there'd be like parentheses here, if that makes it easier to think about, like we're saying sine of 2 times x, where 2 times x is our angle. That's going to come up a lot in the next section dealing with that. So, sorry, spoiler alert. All right, so if we look at our identities, the first thing that's wrong here is sine, sine, cosine, cosine. That is not an identity. In our identity, cosine comes first, and sine comes second. In the cosine identity, which is the one this is most closely related to. So if we rewrite this, we've got minus cosine x cosine 2x plus sine x sine 2x, but it doesn't match our identity. Our identity needs to have the minus sign be in the middle. So what we're going to do is we're going to factor out the negative.
And we're back. So
told you you'd be right back. I actually said BRB.
BRB.
All right, so let's see here.
What are we doing?
We are doing sum and difference formulas.
Oh yeah, okay, right on.
This is now the cosine one.
Right.
And so because this is a minus sign,
we're going to add the angles.
So that gives us 3x inside. We don't really need that extra parentheses. This would just be negative cosine of 3x. That one was a bit on the tricky side right there.
A slight skosh, but if you pay attention to what's going on, you'll start catching some of these patterns. It's all about trying to find the right pattern in there.
Right.
Brilliant.
Example 4. It says proving reduction formulas, and just so you know, a reduction formula is a formula designed to reduce the complexity of an expression.
I thought hey, proving reduction formulas.
Yeah. We starting over now.
We'll start over again. Ready, and you go.
Example 4, proving reduction formulas. A reduction formula, I don't know if you know this, is a formula that reduces the complexity of an expression.
Shut the front door. I thought a reduction formula was like when you reduce something.
That's what I just said.
Oh.
Okay, now that we've got that straight, here are some reduction formulas. And they're handy-dandy formulas. They're kind of like identities. We just don't use them as often, so that's why we don't list them on our circle card. So to prove A...
And, by the way, we can prove these fairly easily, so it's not like we're going to have to do some wacky, crazy thing here.
No, it's actually a lot like example 2 was,
right.
Which you missed out on. Because,
but I will relive it.
Okay, so we look at our sine sum formula.
The sum formula, yep.
Where we've got u and v.
So we're going to have sine x cosine pi. And then sine stays the same. Yep. And then cosine x sine pi.
And then we just have to figure out what is going on at pi.
Which you need to have pi pretty much memorized.
Pi would be a good thing to memorize.
Yeah, and so the cosine at pi is -1. So that would be sine x times -1, right?
Indeed.
Yes, and then the sine at pi is 0, so that's cosine x times 0. So
anything times 0 is 0.
And it doesn't matter that it's cosine x. That's not the point. Anything times 0 is 0. So whatever the x is times 0 will be 0. It goes away.
And sine x times -1 is a negative sine x, which is what we were going for. So we can say happy
Minecraft smiley face.
Proof day. All right, then
same steps on the bottom.
Part B. It's almost the exact same thing.
Except cosine now. So we're going to look at the sum formula for the cosine. And remember with cosine, if we're going to add the angles, we're going to subtract on the sum side.
Indeed we are.
Indeed.
So cosine of x, cosine of 3 pi over 2 minus sine x, sine of 3 pi over 2.
Okay, now cosine of 3 pi over 2, that's another one that you need to have those quadrantal angles memorized. 3 pi over 2, the cosine is 0.
Or if you can quickly visualize in your head
where 3 pi over 2 is, yes. So we're going to have cosine x times 0. Well, that goes just like the previous statement in blue up there in the lighter blue. So he's Dunskies.
Yeah, sine x times the sine at 3 pi over 2 is a -1.
Right.
But since it was already a negative sine x, then we're going to have a change situation.
So that's going to be...
Well, nope.
No, there's no cosine there. There's no cosine. There. But it would be plus sine x.
It would be a positive sine x. And we're done with that proof.
Minecraft dude. I think we should have a guest star.
You do right now?
Yeah, like on our next one. I think we should have a guest speaker.
We'll see what happens.
Hey, prove this reduction formula.
Example 5, tangent. We have a guest star.
Say hi to Miss Steele, everybody.
Hi, guys.
She used to teach math once a long time ago. Yeah?
Yeah.
No? Where are you going? Mrs. Steele, where are you going? Okay. So, we got that trig identity. Let's use it.
The tangent one?
Yeah.
Okay, let's use it.
But I don't know. I don't know if it's going to work.
Because why?
My big toe's starting to hurt.
Okay, well, let's think about this. We have 3 pi over 2 that we're going to have to deal with, right?
Right.
And so down here at 3 pi over 2, this is the point 0, -1. If we're trying to find tangent of 3 pi over 2,
right?
Which if we use the
sine over cosine.
If we use the tangent formula, we're going to have to do that at some point. That's -1 over 0.
Can't divide by 0.
Which is undefined, so we can't use the tangent one, which is why I spoiled it earlier and mentioned that we could change it to sine over cosine.
Sorry, I had to wet my whistle. So here we go, sine over cosine, and we're going to follow that now through the rest of the problem. What should happen is it should work out nicely.
Yeah.
But we also have to keep in mind that, you just can't, 0 in the denominator is absolutely forbidden.
So we
have to look at a different way to maybe work around that.
Right, we're going to actually use both the sine and cosine identities.
Right.
For sine, we would have sine of theta cosine 3 pi over 2.
Minus
cosine
and then swap them.
Theta sine 3 pi over 2.
And then on the bottom, you're going to have the cosine version.
Right, so cosine theta cosine 3 pi over 2.
And then this time it's a plus because it's an opposite symbol, opposite sign, S-I-G-N with cosine every time.
Right, sine theta cosine 3 pi over 2.
Now what we have is a situation very similar to some of our previous examples where we can actually find the sine and cosine of 3 pi over 2. Like, that's information that we know.
Number
like,
that
we have that.
The cosine of 3 pi over 2
0.
is 0. The sine of 3 pi over 2 is negative 1. And then on bottom, we are basically filling in the same information, even in the same order, right? Cosine of 3 pi over 2 is still 0.
Right.
Plus sine theta.
And then the cosine of 3 pi over 2?
No, I wrote this
Something
wrong.
That should be a sine 3 pi over 2.
I lost the
That's okay.
eraser.
Sine 3 pi over 2?
Sorry, sine 3 pi over 2. That's why you gotta pay attention to
Yeah, you gotta pay attention. Yep.
You just have to do it. So gotta be careful here canceling out, because sometimes we like to cancel things out that we're not allowed to. This is 0.
That and 0, which means but we are not canceling those items out.
No, we're saying this is 0 and this is 0.
Right. So 0 minus.
Yeah, 0 minus cosine theta times negative 1 becomes
which is
positive cosine theta.
Right. And 0 plus sine theta times negative 1 is
negative sine
theta.
And if at this point you're confused, look back at what we're trying to get to. We're trying to get negative cotangent. We've got a negative. Cosine
Victory
over
dance.
sine is cotangent.
You should.
I'm not going to circle that.
No, what are you doing? It's Minecraft guy. You gotta also, when you can get a proof to work out, you have to do a little bit of celebrating. It's just it's what you need to do some celebrating. It's what needs to happen. Are we dithering? What was that?
I was trying to erase, but I can't find the eraser.
All right, good.
So
Okay, good talk.
move.
Hey, I think this is perhaps one of my favorite trig problems of all time.
You know, I think that it is one of your favorite problems of all time, because you've told me numerous times. In fact, just a moment ago, you said that you would marry it if you could.
Why would you say that while we were recording
and then
the lesson?
You would have pretty trig babies with this problem. So the code word is going to be trig babies.
Wow, this is almost awkward for me.
But not quite.
That you did that. That's
all right. We, in an earlier section, we graphed these and basically figured out what A, B, and C were from the graph.
Right, by looking at the graph.
But now that we have some difference identities, we can find this out using our identities and algebra and
get an actual exact answer
value
for this.
Yeah.
Now, if you rewind to that lesson and you graph what you get from doing your lining up all your different things, you will discover that your graph is not 100% identical.
Because your calculator is
because the
actually
calculator
rounding,
it's
right?
creating an error.
Yeah.
However, when you do this bad boy, it should be the exact same.
Right. So
let's dig in.
We have this sinusoid that has a sine and a cosine. Wants us to write it in this form. And basically the way we start working this out is we take what we're trying to write it as, and we use the sum and difference identities on it.
Right.
Where this would be, the bx would be u, and the c would be v.
So we're going to have bx takes all the u spots, c takes all the v spots, and you leave that a in front because it's a times the sum or difference of the stuff.
So we've got sine of bx, and then cosine of C
plus
cosine of bx
plus sine C.
Not plus,
times sine C. Yep.
Okay, now this can be a little tricky. So what we're going to do, we're still messing with this to basically make it look like this right here.
Right.
So we're just going to move some stuff around. We're going to distribute the A.
Right.
My B's look kind of like sixes, but
they are
not
sixes. That's critical to understanding.
Yes. And then I'd like to do one more rearrangement. I would like to move it to where the sine bx and the cosine bx are last.
Okay, that sounds great.
Here, that's going to correspond with this x here.
That's right.
Inside of that.
Okay, that sounds perfect. So let's do it.
So A cosine C sine bx.
Now, here's the cool thing that you probably aren't going to catch right off the bat until you've worked this a couple of times, and you will need to work this one a couple times. The x is the only thing in here that's a variable.
Everything else
A,
is
B, and
numbers.
C will all be numbers. So when we say A cosine C, that is a specific number like 2 or 17 or negative 35. We don't know. We're going
Right.
to find it. But
Right.
A cosine C is a specific number.
Right, and so is A sine C.
And, right.
It's actually a specific number.
That is correct.
So because we're trying to write 2 sine x plus 5 cosine x as this, we're going to set these equal. And then look at what things we may be able to match up. So in front of our sine x, we have A cosine C, we have 2, which means that we can say that 2 equals
A cosine C. Yep.
Okay, we're taking what's in front of sine x and what's in front of sine bx, and we're saying those are the same.
Right.
We also really can say then that right here, that's written kind of badly, but it's 1x, and this is bx, which means b equals 1.
There's your first value
Yeah,
right there.
we know b is 1 because there's nothing in front of these x's.
How many x's do you see in there?
If it was 2x,
it would be b equals 2.
Right. And then right here, this 5 goes with what's in front of cosine.
C.
So 5 equals A sine C. Now, go ahead.
And notice here in this case also the 5 cosine x, it's 1x, which corresponds with cosine bx.
Again, yeah.
And
yeah,
again,
these
b
are
would be 1.
ones
Well,
in both of these
we
cases.
determined that already. So b's 1 the whole time through.
Yeah. Now, there's a couple different ways we can go about it. The book does something that I don't think is necessarily intuitive. So I like to look at it this way. See what you think, Mr.
Okay,
Hazelwood.
all right.
We can solve this for cosine C by dividing both sides by A.
All right, sounds great.
Okay, so that cosine C equals 2 over A.
Right.
We all know that cosine is adjacent
Over hypotenuse. Okay, yep,
so
I agree with that.
we can say, hey, look at this I'm going to draw the triangle over here where
All
I've
right.
got some space.
Okay, do it. So we'd say
So
A is a
if
hypotenuse
this
in
is
this
our
case.
angle C, then the adjacent side is 2,
Right.
and our hypotenuse is A.
Okay, that looks great so far.
Okay, we can do the same thing with this one. We can divide by A on both sides and get that sine C is 5 over A.
Oh, looky there. So I know that
So-
one leg is 2 and the other leg is 5.
Right, because this is opposite over hypotenuse.
Right, okay.
Okay,
I'm
which
with you.
means that to find A, because we want A, B, and C,
I can use Pythagorean's theorem.
Pythagorean's theorem.
Aha! Well, that's a little tricky piece of trickiness.
Yes. So that's 4 plus 25, which
It's
is
29,
29.
yes.
So square root of 29.
Hey, I like that.
The way this works is that technically we could have a positive or a negative square root of 29, but we choose to make it positive.
That is correct, yes.
Okay, so we're
Right.
going to choose for this to be positive square root of 29.
Right.
That is what A equals. We've
Right.
got A and B. Now we need C. So what we can do is plug it into either of these formulas.
You get to pick it. That's the
Right
beautiful
here.
thing.
And so that does mean there's actually like 2 answers
Right,
that are acceptable.
right.
Or instead of there, this actually would be better. One of these two.
Oh,
right?
you know what? You're right. Yes, let's go with the cosine C part down there.
equals 2 over the square root of 29. And so to solve for this C, we do the inverse cosine.
Right. And so this is where, as a high school kid, you look at this and you go, oh my gosh, that can't be the answer. I need a number. Ah!
Yeah.
But that's your answer. The arc cosine of 2 over root 29 is what C is. That guy is your answer. Like, that is an okay thing to have.
We've got A, B, and C. We just need to fill it in up here
Yeah.
to what our actual formula is.
Right.
So, well, I used f of x. So, all right, f of x
Equals.
equals A,
A, which is
square root of 29.
times,
Oops, right there.
yep,
Times sine,
the sine
open
of
parentheses,
bx.
B
is
is 1.
1. Okay, so x plus c. Now, c is that whole arc cosine thing, so you have to include that whole guy in your answer. Now, this is one correct answer.
The other correct
The
answer.
other correct answer would have the arc cosine of 5.
No, the arc sine.
The arc sine of 5 over root 29. That's the other way that you could have this. So both of those would be correct.
If we had solved this for
Right.
C, we would have gotten inverse sine of
5 over,
5 over.
yeah, root 29.
Yeah.
Yep. So that's the other one that could be down there where the arc cosine is.
Okay,
Now,
that's a tough one.
that's a tough one, and having worked through this, I will tell you, this is one of my favorite problems. because it requires you to use all of your different trig knowledge.
And just a BT dubs, when a teacher says something is one of their favorite problems, it usually means that it's guaranteed to be on the test.
So practice this a couple times, and you'll start seeing some habits that you can form,
Yeah.
and some tendencies that occur,
It's
and then
not
you can
always
take
this
those same
hard.
steps.
If you can, for example, remember this right here instead of having to derive it every time, or if you can remember this instead of having to even mess with the stuff up here. Once you get the hang of it, it's not as bad.
Right, but it does require some practice.
Yes, it does.